First of all, let me remind you briefly what we did last time. Basically, we defined Brownian motion on RD. It is important for us what we obtain, the whole construction. Yes, what we obtained, so I will repeat. We obtained that we have a probability space, and we have where omega was actually equal to the set of all continuous function with values in RD, and F was, I will just write that it's Borel sigma algebra because we already know it's the same as cylindrical. On this metric space, this is metric space as we know with uniform Actually, no, it's metric space not with uniform continuity of complex. Yes, but it's still metric space. It's useful to know, but it doesn't matter now. It can be unbounded if it's to infinity, but on complex we can still say that we have metric. And okay, it's not important now. Maybe I shouldn't say. Sorry. So now we have Borel sets on this cylindrical sets or Borel sets, doesn't matter. And we have Px. Px is such that if we take xt, what is xt? Maybe I did not explain it properly, but we just take xt as so-called coordinate functions. Yes, so we just also useful to write them as xt omega. Yes, so they belong from this is RD valued functions from t and from omega, where omega belongs to omega large. So omega is continuous function, and we take its value at some point t. Right? So this is xt. Xt in this probability space. This is on this probability space. It is a stochastic process. Right? And it is important that Px is such that xt1 and so on, xtn for each 0 less than t1 and so on less than tn, for all different t1, tn greater than 0, this has distribution with density p t1 x1 minus x multiplied and so on. I will not write it down too detailed because I already know this. Yes, where again xn minus 1 here, and p is of course Gaussian density. One more time. Okay, so this was the definition, and we last time we actually proved that this such px exists. Yes, for each x, such px exists. And you may have noticed that we have the same space, the same sigma algebra, but potentially different px. This is a typical for Markov processes, but we will not talk about Markov process in general. So we will only talk about this process. But what we actually need is some properties that are typical for Markov process. Yes, and for example, Markov property is what we need. So next we will talk about the Markov property for this process. Of course, there are very different many forms how we can write down what is called Markov property. I will remind you of some ways, and then we will prove one of the variants which would be most useful for us. Okay, let me start from this one. This is often in some textbooks. You can see that Brownian motion called having Markovian property because of the following. If we take for each fixed u, if we take xt plus u minus xu, t greater than or equal than 0, then it will be equal in distribution to this process started from 0 at 0. I will just write it like this, but it also kind of means that we set x equal to 0 in this picture. Yes, because in this picture, as you can see, x enters here as a starting point. Yeah. And because of that, here, because I subtract the starting point, I have to subtract it here, but we have such identity. It is easy to check using just this distributions. Yes, finite dimensional distribution. We check that finite dimensional distributions are the same, which is exactly means the distributions are the same. Yeah. And so this is well known. And moreover, this one is independent from everything that happens before moment t. Yes, it's independent from xs s belongs 0u. Yeah. So, and this is what usually often called Markov property for Brownian motion, but it is just property of Brownian motion, which is very useful in some calculations. Unfortunately for us, this is not quite enough. Why? Because we need to some corollaries from that. We need some equalities with expectations which follow from that. And this is what we're going to do. We're going to study such equalities, and we're going to have to prove them because they're not immediate from what I've written. So we'll have to prove them. Let me start from giving you another version of Markov property, which let me write down. Let me give you a definition of ft again, although we've already seen it, but I still write it down again. S belongs from 0 to t. Yes, so this is sigma algebra generated by all values of a function before the moment t. Again, we're working on the space of continuous function as a probability space. Yes. Okay. Using this, we can write down the following. The probability px, I will use probability for arbitrary x. For any x, yes, for any x, we have the following: xt plus s, and for any t greater than 0, for any s greater than 0, and for any Borel set A in Rt, we have the following. This belongs to A, given if t is the same as pxs, sorry, t, because of t here, right? Probability that xs belong to A. And this should, you can see that both left and right side are random variables, so I have to add almost surely px. This is conditional expectation, of course. And again, what happens here, if we take some moment t and some moment t plus s, yes, we have a Brownian motion. So it is claimed that if we take conditional expectation of what happens in this moment t plus s, then it is actually just expectation what happens at moment s, but with starting point xt. xt is the starting point. Yes, for the Brownian motion when we calculate this probability. And this is also Markov property. It is already closer to what you know, probably. Yes. So here we already have the well-known. We can see the well-known Markov property, which is everything that happens after moment t depends only on what happens at this exact moment t. Yes, and here we can see that this conditional expectation, which describes what happens after the moment t, if we know what happens before moment t, is actually depends only on xt. Yes, it does not depend on anything else before moment t. So this is one of the classical ways to write down Markov property even for general Markov processes. And even already here we have a kind of slight problem, technical. If we want to obtain it, for example, from what we know, yes, we need to prove this equality, and we need to write down the definition, for example, of conditional expectation, and then we will have to take for either we have to take indicator of A, or we have to take some bounded random variables, yes, and then we have to prove the equality. If px is probability, then ex is expectation. Yes, so ex is expectation, which relates to px. I will use it from now on. So what we have to prove is that indicator of xt plus s belongs to A, or indicator. Okay, I will already write in this form xi equals to ext, again using expectation, corresponding expectation to the corresponding probability. Indicator xs belongs to A, and here xi. Yeah, so this is one of the definition of the conditional probability, is that this equality should hold for all xi that are measurable of t and bounded. It's exactly what I written, but I repeat. Yes, and this is of course almost surely px. Also written here. It also should be written here. Okay, so this is what we have to prove, right? To prove this. So we have a problem here because we need to be able to put any xi here. And this is in this point we need some approximations. Yes, so we need to approximate xi with something in order to be able to do this. Will be the point in the following, but I also need more general form, even more general form of this than it is written here. So let me do first generalize it even more. What is possible? One more possible way to generalize it is to write something more general instead of this. Yes. To do that, I introduce the following map. It is called shift transformation. It is a map from omega to omega. I again remind you that omega is a space of continuous function. Yes. So theta t from omega is defined at point S. So we map functions into functions. So this function at point S is the same as this function at point t plus S. So what happens is we take some continuous function, any continuous function, yes, we can take, and then take some point t, and then theta t acts like this. It transforms it into just this part, and this will be starting from 0. So I may have drawn it a little bit differently, but it's just believe me that it's the same. Okay, it is the same part that's here. So we just cut down the beginnings and say that we start from 0. Is there any questions here? Okay, so if we do this, what we obtain the ability to write down more general form of Markov property, which looks like as follows. We can also define if xi is some random variable on our space. Yes, this xi belongs to F means that xi is a random variable measurable with respect to the sigma algebra. I hope everyone knows this notation. So if we take any random variable measurable our sigma algebra on the space of continuous functions, then we can define theta t acting on this xi as follows. This from omega is the same as xi from theta t omega. So what does it mean? So if xi somehow depends on trajectory, so we take some points of trajectory, do something with them, and so on, and produce xi. Yes. So what we do with what is theta t xi is we do the same, but only with trajectory starting from point t. So we do the same as we did with a normal trajectory, but only starting from point t. Yeah. So xi is actually kind of functional from everything that happened after moment t. Yes. And it works in the same way as it would be applied to the normal trajectory from 0. Yeah, for shifted trajectory. Again, this shift works like this. Yes, so we shift like this. Okay, what does it mean? It means that we can write down the following expectation theta t xi. Suppose that xi is also bounded. Theta t xi, knowing if t is equal expectation xt xi almost surely px. So what happens here is we take something that happens after the moment t. Yes, xi t xi is something that happens after the moment t. Let's say that this if the same happens after 0, then we basically averaging we have the same. Yes, if we start from xt. Okay, maybe I did not explain it well, but it is a generalization of what we just did before with this Markov property in this form. Yes, so instead of this form, we have some kind of general functional inside of expectation, more general function. But in order to formulate it correctly, I need to say that this functional is shifted by time. Yeah, here like this. Do you have any questions in this part? Okay, so now finally, I remind you of one more definition. U greater than t, ft plus, yes, fu. This was the definition. Finally, I can formulate theorem, which will be our general form of Markov property. Which will look as follows. For each t greater than 0, x belongs to Rd. For any psi measurable and bounded we have the following expectation. I will write down almost the same as before, except I can also write ft plus instead of ft. It is very interesting modification of this. Will be somewhat useful in the future. xt psi almost surely px. Okay, do you have any questions on this formulation? Good. So right now our task is to prove this general form of Markov property for Brownian motion. Again, I already told you. So the main way to do this is approximate everything. So approximate xi and approximate that eta that appears in when we write down not eta but some another random variable that appears when we write down the definition of conditional expectation. Yes. So this will be the main idea. How we can approximate? We can approximate with functions of form f from xt1 and so on xtn. So this will be approximation for xi, for example, or for something that we have to multiply on. Yes. So this is a typical approximation, and in what way we can approximate? Yes. Let us think about it a little bit. What if psi n converges to psi uniformly on what does it mean uniformly? It means that supremum for all omega, cn omega, yes, minus psi omega belong converges to 0. It seems a little bit odd that I use uniform convergence on the probability space, but it is for this task when we need to approximate. It is actually okay, because our approximating quantities can be made. There is no probability in this picture. Yes, when we want to approximate some measurable, originally there is no probability. Of course, then we plug it in the expectation. But originally we can look at this like this. So we have some function. Yes, this is just functions. So we can actually bounded functions. Yes, and bounded measurable. Yes, some kind of bounded measurable functions that converges to psi in this form. Then I claim that if this satisfy each psi n, then psi also satisfies. So what I claim is that such kind of convergence, it conserves this property. So if we prove it for all for some set, then we also can prove it for its closure versus such operation of uniform continuity. This is very good for us, but it's not all because, as you know, uniform continuity is very strong and it's not enough. We not always can approximate with uniform continuity. We also need convergence, sorry, and we also need monotone convergence. And I will specify what is monotone convergence. We will say that xi n have a approximate in the sense of monotone convergence some random variable psi if psi n greater than 0, if they are universally bounded. So for any omega, for any n, uniformly bounded. Yes, there exists constant. There exists constant such that for any omega, for any n, they are bounded. So they are bounded uniformly, and they converge to some psi monotonously. So it means that psi n will be less than or equal to psi n plus 1 for all omega. Yes. Is there any questions to what is monotone convergence? Okay, so in here it is very good for us that if Xn satisfies this condition, then psi also satisfies this condition. So monotone convergence also conserves this. Why it is so? Well, it is just bounded, Lebesgue bounded convergence theorem. Everybody should know that, right? Since we have them uniformly bounded, then it's not a problem at all to have such. So this property also kind of closes under operation of monotonous convergence. So what we need to do to approximate is to approximate our general Xi with monotone and uniform convergence. So how do we do this? I want to give you one general theorem that is very useful specifically in the potential theory for some reason, and also will be useful for us here. So this is monotone class theorem. There are many theorems that are called monotone class theorems. They all have the same form, which I will show you now, but with different conditions. This one in particular is from the book De Meyer. This is Probability and Potentials. If anybody knows, this is a very good book in the sense that it has all the basics that you ever need. It is very, very detailed. It is hard to read maybe, but it's very detailed and very well written. Could be hard to read. This is a problem, but if you want to study potential theory, you have to look at this book at one point or another. And they have a very nice monotone class theorem that we are going to use. So let me formulate this. Suppose that H is a linear space or vector space, whoever likes this notation more, but it means that H is contains vectors. Yes, so we can add them, we can multiply them by some constant, yeah, and they stay in the space. And this will be the space. This will be a real space. So the constants will be real. But this is also a space of bounded real-valued function. On some set, yeah, it doesn't important what is the set E, but we have some set, and on this set we have a linear space of not necessarily all, but some bounded real-valued functions. Okay. And suppose that this set is closed under, suppose H is closed under uniform and monotone convergence, exactly in the sense as I showed you before. So uniform convergence is just supremum convergence. Monotone convergence is like this. We have Xn greater than 0 and such that, and then if Xn belongs to H, it means that Xi belongs to H. Yes. So this is exactly mimics our situation in that sense. Okay, and next, suppose that C is a subset of H closed, which is closed under multiplication. Okay, and then turns out this is enough to claim that then H contains all bounded functions measurable with respect to sigma algebra generated by C. Just in case, I will also write the definition of this. This is sigma algebra generated by all sets of the form X belongs to E, such that F with X belongs to some set A, where F belongs to C and A is a Borel set. So this is just sigma algebra generated by the preimages of F. Okay, preimages of Borel sets with F. Of OF in this C, set C. Okay, but why it is this theorem is useful for us? Because if we said if our set C is exactly the set of such functions in this situation, and if we it is closed under multiplication, obviously, and if we yes, we can also state that if it's bounded continuous, it is enough, right? And then under this theorem, H will be all such psi that satisfy this equality. Yes, and it will be a linear space. It will be, as I mentioned, closed under convergences of both uniform and monotone. You see that this equality is actually linear from psi. Yeah, it is very useful. Now we use it. So then the theorem claims that actually this equality holds for all psi measurable with respect of sigma algebra generated by such functions F. And of course, the sigma algebra generated by such F is just cylindrical sigma algebra, is the same sigma algebra. So we have all psi measurable here, yes, with F, all bounded measurable, yes. So this is exactly this theorem. If we apply it directly here, it's maybe what we need. Well, I will give you the full proof of theorem later, of course, but this is what we need for now. So now what we have to do is to prove this. Yes, let me prove this. I'll call it theorem 2. Yes, I'll call this theorem 1. So we first prove theorem 1, then we prove theorem 2. Sorry, proof of theorem 2 first, of course, and then theorem 1. So let's consider algebra generated by constant. Okay, I'm sorry, I forgot condition here. This is bad. So here constant has to belong to the H. Yeah, so this is oh, by the way, it is interesting to compare this theorem with some other theorems that you know. You probably already know, yes, for example, Weierstrass theorem that you already mentioned to me when we approximate continuous functions, yes, uniformly. And there are also some theorems like Stone-Weierstrass theorem in the same direction, yes, for approximation of continuous function. There are also theorems that let us approximate any function in L2 in 0, 1, yes, with the back measure, with some indicators, some sums of indicators. Yeah, probably some of you know those theorems. What is the difference of those theories and this theorem? This theorem, there is no, there is a different space. We have a space of bounded measurable functions. In the Stoneway-Strass theorem, we have the space of continuous functions. And we have a continuous norm, of course, here. And in L2, again, we have L2 functions that are integrable, and we have L2 norm. Here, no conditions on the functions except measurability and boundedness. So the spaces are larger, and this is different. So we have, it is slightly different, but it's similar. Maybe you can prove some other theories from this, for example, or vice versa, but it is a slightly different theorem. So keep this in mind. This has relations to this, for example, Stoneway-Strass theorem, but not direct ones. So it's not exactly the same in some ways. And of course, there are other variants of this theorem with different conditions. So back to the proof. Take algebra generated by constants, constant by 1 and C. Yes, so it is important here that 1 belongs to H, so that this algebra generated by 1 and C will actually belong to H. It will belong to H because of these properties, yes, that C belongs to H. So any multiplication is just either multiplication of constants or just inside C. So multiplication does not take us outside of H, and all other properties like addition and multiplication by constant is already leave us in H because it is linear space. Okay. So this, by the way, do you know what is algebra generated by? Do I have to say this?
Minimal one.
Yeah, no, probably you can say it like a minimum one, but I think it's enough to say that it's just some finite linear combinations of the products of elements from the generating set. It's probably should be enough, right? Because it is generated as finite sums and finite products. Okay. So let's suppose we have such algebra. Then the next step is we take B to be maximal algebra such that of all algebras such that it is between this C tilde and H. How do we find such maximum, or how do we prove that such maximum algebra exists? Maybe some of you know some statement called Zorn lemma. Let me formulate it because I have suspicions not everybody familiar with this. Suppose that we have a partially ordered set. What does this mean? It means that we have some for each x belongs to m, y belongs to n. We can have that x greater than y, or we can have that x less than y, or we can have that there is no such condition or such condition. So they might not be comparable at all. So it is also possible. It means partially ordered set, and of course, what the order means that if x, y, z are such that x less than y, y less than z, it means that x less than z. Yeah, typical condition. So this is partial order, and suppose that for any n that is subset of M, which is ordered with this order. What does it mean? It means that for any x, y in n, we have either x not equal to y. Yes, I will not touch the situation where they equal. We will not compare the same element with itself just at all. X less than y or y less than x. Yes, either this or that. So means that on n we have a full order. This order becomes full order. So this is just an explanation what is ordered. But the statement is for each ordered we have a upper bound. So there is such x belongs to m, so that for any y in n we have y less than x. So we have such element that is greater all of the elements in n. So if this is true, then there exists maximum in M. So there exists such x belongs to M, so that for any y in M, x greater than y. Do you know such, this is Son lemma. Do you know such Son lemma? Are you familiar with that?
It's used to prove Hahn-Banach theorem, I guess.
No, it's either way around. I think Banach theorem is consequences of that. Consequence of this. Okay, so let me say a few.
It's what I'm saying. Yeah.
Yes. Okay. So what essentially Son lemma is? It is equivalent to so-called axiom of choice. Yes. So when we build set theory, then we have to make some assumptions. And one of these assumptions is axiom of choice. That, if we choose one element from the collection of sets, then we obtain a set. It does sound natural, yes, but in fact it is equivalent to such already non-trivial statement. It is very useful for us now. Why? Because this maximal algebra is exactly maximal element in the set of all algebras. If we take all algebras such that it lies between C tilde and H. We have at least one element in this set, which is C tilde, and it is partially ordered by inclusion. So our order is just an inclusion here. And it is easy to check that if we have ordered set, yes, we have an ordered set, subset of M. Then if we take union of OA belongs to N, this is actually algebra. Why it is so? Because if we take, for example, multiplication of two elements in this, then these two elements belong to some two different A's. But since the set is ordered, then one of these A's belongs to the other. So they all belong to some one set, to one A. And this A is also algebra. So they belong to, the multiplication belongs to this A, and so to this union. And the same with addition and so on. So using Son lemma in this way, we obtain that we have to have maximum element by inclusion in this set. So we have to have maximal algebra, which means that any other algebra will be subset of this. Any other algebra satisfying this will be subset of this algebra. Good. So we have such object, and now we start working with this. We say that first of all, we say that B is closed under uniform convergence. Why is that? Because H was closed, and now if we suppose B is not closed, so suppose that Cn, okay, Fn, which are uniformly convergent to F, and Fn belongs to B, yes. So what we do is we look at the algebra generated. We know that f belongs to H, by the way, since Fn belongs to B, so we can conclude that f belongs to H because H is closed under this. And so that when we take B and F and generate some B square, sorry, B tilde, yes, which is algebra generated by B and F, I claim that B also, we take algebra generated by B and F, and I claim that it also belongs to H, which means that F also should belong to B, right? Why it belongs to H? Because what we have to check? We have to check that each element of this algebra belongs to H. Sums with F and any sums, if we take sum F plus G, for example, yeah, where G belongs to B. Why it belongs to H? Because it is a uniform limit, yes. Same with F multiplied by G. It is uniform limit. And H is closed on the uniform limit. So clearly, whatever we do in the algebra, we cannot go, when generating this algebra, we cannot go outside H by the definition of F. Is this clear? Is this clear why this is closed on the uniform limit? Okay, so I also claim that E is closed on the monotone convergence. Why is that? Why is that? Let me look again at this picture. Yes, what we need to do is we need to prove that okay, if any sum have uniform have monotone convergence, if Fn has monotone convergence, then sum probably also have monotone convergence. Yes, but with the product we have a problem because when we multiply by a function, this function can change signs, so we cannot just say that if Fn converges monotonously to F, then this product also converges monotonously to F. In order to overcome this difficulty, we need to prove the following: that actually, if G some G belongs to B, it means that its modulus also belongs to B. From this, we will have that min max also does not take us away from B. So if G1 G2 belongs to B, then maximum, for example, belongs to B. Yes. Same with minimum. So this is what we need. If we have this, then it is obvious. Then we have here we can write down this as G plus minus G minus, where obviously G plus is maximum G0 and G minus is minus minimum G0. Yes. So this is two positive functions, and for each such non-negative functions, for each such non-negative functions, we can transfer, like we transferred uniform continuity, we can transfer monotonous convergence also. So all we have to prove is this. Is there any questions to this? I have to say that this is, of course, very involved theorem, but it is very useful. That's why I'm doing this. Okay, so now to prove this, we recall again that Weierstrass theorem. So on minus CC, we can approximate there exists for any epsilon greater than 0, there exists Pnx polynomial. It doesn't matter if it has coefficients in rational coefficients, but it does not hurt, right? So what's important is that it approximates uniformly modulus. We can always find such polynomial. but B is algebra. So polynomial, this polynomial, or if we take G, then any polynomial will belong to algebra. Yes. And we can take C such that C is just supremum of G. Yes. So that it happens, so that in fact P and G converges uniformly to G. Sorry, Pn. I have to. Yes. I'll take N here. Yes. I'll take N for any. Yeah, I'll just have to make sure that it converges. So I can do this like this. Yeah, it's okay. And so now it converges, and we can see that in fact to modulus of G. Yes, and we can see that this belongs to B by the previous claims that we were close to the uniform convergence. And from this, it follows that it is close to the monotone convergence. Okay, and this was the hard part, the hardest part probably. So now we can say that since base B is close to the uniform and on the monotone convergence, then it is in fact what we need. So we take a set S is a set of all subset of E such that indicator of A belongs to B. Again, what we do we know about S? S is closed under finite intersections and operation of sorry, I forgot how to call it. So it is closed under, for example, if B1, B2 belongs to S, it means that B1 intersection belongs to S. Yes, and if B1 and also that E without B1 also belongs to S. Complement, yes, complement. It is closed on complement, and also it is closed under monotonous convergence. So S is in fact monotone class. You should all well know that it is well-known theorem that such S is actually sigma algebra. Yes, this is sigma algebra. And all we need to prove that S contains all the sets of form S contains sigma C, right? In fact, yeah. In fact, it is enough to prove that it contains all the sets of the form X such that X f with fx greater than 1 and f belongs to C. So this sigma, why I can take 1, because we know that if we take anything else, then we can just multiply function f by some, and we still have the function that at least in C sharp, so it doesn't hurt us to just consider this. And so if we only have to prove this, and now the final step is to prove that this belongs to S. We note that if we take function f and we take it minimum f0, sorry, maximum minimum f1 f0, this is so-called trim. So we have a function and we trim it so that if it less than 0, it's 0. If it greater than 1, it's 1. So only what happens between is important. And then this call it function g, and note that g power n converges monotonously. Well, it actually not increasing but decreasing, but that doesn't matter. To indicator of the set f greater than 1. So since this function belongs to B, right? Okay, maybe I should write B here, but it's the same. No, I have to write C here. So it is enough that S contains of this. Yes, and if I prove that it contains of this, it's even better. So if G belongs to B for sure, and G power n also belongs to B, and it converges monotonously, so this also belongs to B. And this is the end of the proof. Is there any question? Okay, once again, the proof is somewhat non-trivial, but this theorem itself is very useful. And as a result, we can just prove we can prove our theorem 1 very fast. Let us do that. So proof of theorem 1. First of all, let us look at the following quantity: expectation x f xt1, let f be bounded, measurable on Rd. And we look at such quantity. I claim that this is continuous function if we consider it as function from x, t1, and tn for all t1 and so on tn, such that they are not equal to 0, and x belongs to Rg. Why it is so? I recall you that this can be written as integral with density. Yes, so we can take fx1 xn and here multiply by density p t1 x1 minus x and so on, and then dx1 dxn. This is the definition of such expectation, yes, because we know this distribution. And then we notice that if t1 greater than delta, t2 minus t1 greater than delta, and so on, tn minus 1 greater than delta, then everything here is bounded, yes. So if the times are different and not equal to 0, with some delta greater than 0, with some distance, yes, then we can just bound. And therefore, we can have bounded convergence. And it is trivial that this is false. Is there any questions to that? Okay, so we proved actually very useful lemma that this function is continuous. And now, to the proof of the theorem, what we have to do is we have to consider two functions, two f of f and f1 will be bounded continuous. They will be in different spaces because we will have space Rm. It will be the number of points for one function. And we have also t1, tn, the number of points for other function. And what we have to do is we have to also say that, okay, it's probably better to write again picture. So we have S1 and so on, Sm. Then we have T plus T1 and so on. T plus Tn. And here, what I need to do is I need to we need to also throw in t plus h here. What does it mean? It means that instead of separating it with some time t, we just shift this time t by some h. And we also, in this way, we make that t can be smaller than fsm, for example. In such a way, we instead of ft, we obtain here ft plus. Yes, this is what why this stand for. This is the trick. So what we need to, what we know, yes, what we know is this following expectation. Sorry, S1, let me do S here. S1, SM, this will be better. F1 from X T plus T1. Yes, and we also take H between 0 and T1, so that T plus T1 will be greater, yes, and this will be like this, like I put in the picture. XT plus Tn will be equal. Here we use just the density, and if we do this, we will note that we can write like this. F1 from T1 minus H, and so sorry, XT1 minus H, of course, XT1, XTN minus H, and what will yes, so this is just follows from the way we know what we know about finite dimensional distributions. Okay, and from this, using this monotone class theorem, we can replace this f with any psi bound, which is measurable with ft plus. You see that it's actually measurable with t plus h. Yes, but since it's measurable for ft plus h, it's also measurable ft plus, yes, and bounded. So we can plug it in here instead of this function by the monotone class theorem. Then if we do this, we can also set h to 0. Not we took it in this set, so we can just put it to 0. You see that nothing depends on h here, so only this will converge, and it will converge because we know that this function is continuous. We just proved it, and the x is also continuous, so there is no problem here. It will converge, and because everything is bounded, we have convergence under expectation too. And after taking limit, we have this. And it's almost what we need. We just need to take one more step. I'm sorry, H was already not here. We already get rid from it. So this only xt1, xtn. So finally, we do one more time. We do the monotone class theorem. Here we can have so that okay, maybe not here, but here we take it to some eta that is just measurable, and here we note that this is the same as right theta t from xt1 and so on fx tn. Sorry, I don't need it, xtn. xtn. Okay. And here we can replace it with theta t eta, again using monotonous class theorem that we proved. And this will be what we need. This will be exactly the statement in this conditional expectation in this theory. Is there any questions to that? Okay, this is all for today. Is there any questions for everything that I did?